Solderless breadboards are essential tools for the electronics experimenter. They allow us to build and rebuild circuits quickly without making or breaking permanent connections. In this video, we will demonstrate the basic concepts of circuit building using a breadboard. For this video, you will need a breadboard, jumper wires, a 9-volt battery, battery clips, a 9 to 5 volt voltage regulator, an LED, and a 1000 ohm resistor, as well as some audio cables and alligator clips. We have laid our parts out on the table. First, we connect the 7805 voltage regulator. The 3 pins can go into any 3 rows. Since we have a switch, we attach the battery. If you don't have a switch, leave this disconnected for now. Connect the black lead of the battery to the ground rail and leave the red lead disconnected. We will show how to connect the switch in a minute. Now the middle pin of the 7805 goes to ground and the right pin to our voltage rail. The potential between our voltage and ground rails is now 5 volts. Next we connect the LED from any row to ground. LEDs are polar, so they must be connected in a specific direction. In this case, the anode lead must be connected to a row and the cathode lead to ground. In almost all cases, the anode lead of the LED will be longer than the cathode. You can use this rule to figure out which side is which. Also, the cathode should correspond with the flat side of the LED. In the schematic symbol, the cathode lead is the side with the line. We have to connect a resistor between the anode of the LED and another row on the breadboard. Resistors are nonpolar and can be placed in either direction. The values of resistors are marked by color-coded bands. There are 2 schematic representations of resistors. This is the color coding system. A different color is assigned to each integer value 0 through 9. The first 2 bands represent a single 2-digit number, in this case brown and black, 10. The next band represents the multiplier, or power of 10, by which that 2-digit number is multiplied. The same values are applied to each color, but this time those numbers represent powers of 10. Black is 10 to the 0 power, red is 10 to the second, so our value is 1000 ohms. Finally, the last band represents tolerance, or possible deviation from the marked value. This value isn't very important for our experiments in this demonstration. We have now connected the other end of the resistor to the top voltage rail. Because we connected our voltage regulator to the bottom rail, we have to bridge the top and bottom rails in order to establish continuity between them. We'll bridge the ground rails first. Connect the top ground rail to a row on the top half of the breadboard, bridge the trough between row sections, and connect the bottom row to the bottom ground rail. For the voltage rails, we'll use a single, longer wire to connect the top rail to the bottom. Because our battery is already connected, our LED lights up. We'll show you how to connect your switch and battery in a minute. Here's how breadboard continuity works. Because our rails are now bridged, we can access ground and positive 5-volt potentials on either side of the board. Always remember that through dividing our board horizontally, the trough represents a break in continuity. Now we'll show you how to connect your battery and switch. The battery clip should be connected to the 9-volt, giving you access to 2 bare wire leads. Don't let the leads touch. The red lead is positive 9 volts and the black lead is ground. Connect the battery lead to one lead of a single pole, single throw, or on-off switch by twisting and taping the bare wires together. The other switch lead should be connected to the left pin of the 7805. The switch now selectively lets current pass from battery into our circuit, turning the LED on and off. Here are a schematic representation of an on-off switch. When switched on, current passes through the 7805. The 9-volt potential from our battery is decreased to only 5 volts by the voltage regulator. This makes our 9-volt battery LED friendly. Here's the pinout of the 7805 voltage regulator. Because the ground lead of our battery is connected to the ground rail, and our ground rails are continuous throughout the breadboard, the middle pin of the 7805 is connected to the same ground as the battery. And because the 5-volt output of the regulator is connected to the voltage rail, and the rail is continuous throughout the board, the resistor is connected to positive 5 volts. This means that current can flow through the resistor, then through the LED, then to ground. This current flow lights the LED. Let's try connecting voltage to the LED using a potentiometer. This allows us to change the amount of current flowing through the circuit and therefore change the brightness of the LED. Connect a red alligator clip to a wire sticking out of the voltage rail. Do the same with a black clip, connecting it to the ground rail. Connect the other ends of these clips to the outer pins of the potentiometer. Now, connect a third, differently colored alligator clip to the middle pin of the potentiometer. Using another short wire, connect the other end of this clip to the resistor. If your power isn't switched on already, switch it on now. Here's the schematic symbol for a potentiometer. And here's its pinout. Now try turning the potentiometer. Notice how the brightness of the LED changes. Since an LED's brightness is determined by how much current flows through it, and because resistance limits current flow, we can control the brightness by turning the potentiometer.